Hi, calculus students. Welcome to the first video notes of a new unit. These notes are going to be on the limit definition of the derivative, which was introduced in class. And then here I'm just going to take some time to go through some examples of how can we use the limit definition of a derivative. Really quick before I get into that, we're just going to summarize a little bit from what we talked about in class. So first of all, what is a derivative? So we talked about two big things. The first one is that a derivative is telling us the instantaneous rate of change at a specific moment. And then the second idea behind a derivative is the graphical interpretation, which is that it's the slope of a tangent line at a point. And so kind of using this idea of can we calculate the slope of a tangent line in class, we came up with our limit definition of the derivative, which is the limit as h goes to 0 of f of x plus h minus f of x all over h. So the idea is we're taking this formula is our average rate of change formula between two different points that are h distance apart. We're saying as those 2 points get closer and closer to each other, or as the difference between them h goes to 0, this limit should tell us what the slope of the tangent is. Okay? And just to kind of introduce some new notation here, I'm going to write the word notation above. So this is our limit definition, but we also say this thing is equal to, if we have some function, we're talking about some function f of x, we call the derivative of f of x f, this is like an apostrophe x, and we say, how we say this is we say f prime of x. And f prime is synonymous with a derivative. So the idea of seeing this notation means find the derivative of your function. How do we find the derivative of a function? We're using this limit definition of the derivative. Okay, so now let's get into some examples. My first example is going to be kind of trivial, or very simplistic. It's f of x equals 7x. I say this is a trivial example because I don't actually need the limit definition to know what the tangent line what the slope of the tangent is, because 7x is a linear function, right? I know graphically it has a y-intercept of 0 and a slope of 7, so it looks something like that. Well, if I think about a tangent line at a specific point, the tangent line just lies along that linear function, right? Because your instantaneous rate of change is constant over the whole interval. It's just the slope of this line. So like graphically, we should know this already. We should know f prime of x equals 7, right? The slope of the tangent line at any point is 7 because this is a straight line. Okay? Now let me show you how we can get to that same answer using the limit definition. So I would say f prime of x is equal to, now I'm trying to plug into this formula. So I'm going to say the limit as h goes to 0 of f of x plus h. That just means this function rule where I substitute in x plus h for the x. So that would be 7 parentheses. Instead of that x, I'm writing x plus h minus f of x. That's just 7x. All over h. Okay. Now, here's the thing. I know that if I do straight substitution into this limit, I plug in 0 for h, I'm going to get 0 over 0, which is indeterminate, right? So I could try that. Plug in, and we get 0 over 0, which is indeterminate. So now what do I want to do? I want to see if there's a way to algebraically transform this, get something to cancel that will allow me to get to an answer. And I can kind of start to see, oh, I could distribute this 7. So now we have the limit as h goes to 0 of 7x plus 7h minus 7x all over h. Okay, so what happens here? Well, 7x minus 7x cancels. So I get the limit as h goes to 0 of 7h over h. And guess what? Those h's can cancel too. So now I have that the limit, I'm taking the limit as h goes to 0 of just 7, right? Well, that, if the limit of a constant value is just, that is in and of itself just 7, right? There's nowhere to plug in 0 because there's no h's, but I still know that that should be 7. And I just want to add that the meaning of this value of 7 is this is the slope of the tangent line at any x value. So sometimes your answer still has an x in it, and then you could plug in different numbers for x to get the specific slope. But since this is linear, then we know that the slope of any tangent line at any point is 7, right? Anywhere along that curve, this line is going to have a slope of 7. So then my answer is 7 for any x value. Okay, let's look at another example. And this one's going to be a little bit more interesting. We're going to do the derivative of f of x equals x squared. So using my limit definition, I say f prime of x is equal to, I want to say the limit as h goes to 0 of f of x plus h. So that means plug in x plus h for the x in the function. So that means x plus h squared minus f of x, which is just x squared, over h. Okay, now basically, like you could do the indeterminates, like plugging in 0 for h every time, but basically this setup will always give us 0 over 0 for any function if we're plugging in 0 for h. So essentially, I'm assuming I have indeterminate, so I don't have to show that every single time. So now I'm thinking, how can I do some algebra here, get something to cancel, and then plug back in? So I know one thing I can do is I can expand x plus h squared. That's x plus h times x plus h. So you could think about foiling that out, or just if you remember the rule for binomial expansion, we should get, this is still a limit as h goes to 0. And now I have x squared plus 2xh plus h squared minus x squared all over h. And notice something cancels right away. I can cancel those x squareds. So now I have the limit as h goes to 0 of 2xh plus h squared over h. And if I plug in here, I'm still going to have 0 over 0. So I really need something else to cancel. And I see that I have h's in both of my terms on top. So I'm going to factor that h out. And then this becomes 2x plus h in the parentheses. And now I see, oh look, now that I factor that h out, I can cancel an h top and bottom. Now this is the limit as h goes to 0 of 2x plus h. When I plug in 0 for for h, I get 2x plus 0, which is 2x. Okay, so what is this telling me? This is telling me that f prime of x, or the derivative of f of x, is 2x. Okay, so this is essentially giving me a formula to know the slope of the tangent line at any point along the graph of x squared. Okay, so then I could ask, like, what's the slope of the tangent at, say, x equals 3? Well, I would just plug in 3 for x into my f prime, and I get f prime of 3 equals plugging in 3 for x, so 2 times 3, it equals 6. Okay, so graphically I know that, like, if you think about this graphically, I know what x squared roughly looks like, something like that, and say 1, 2, 3. Say here's the point at 3. The slope of that tangent line is 6. Okay? And clearly, like, if we picked a different point, we should get something different, right? Like if we picked negative 3, I would get 2 times negative 3, which is negative 6. And clearly, like on my graph, that has a negative slope over there. Okay, we're going to do a couple more examples, at least one more example. Let's see. So in my next example, I'm actually going to do it two ways. Okay, so suppose from the beginning I said find f prime of 2 given, say, for some f of x function that is 4x squared plus 5x. Okay, so we actually have two options here. One option is to do this exactly the way we just did example 2, where we first find the derivative in general for any x, then we plug in the value of 2 at the end. But there's actually a way I can do it where I start with plugging in 2 and I get a specific answer. So I'm going to show you both ways. Way 1 is going to look a lot like the previous example. And I would say either one of these is perfectly acceptable. It just kind of, you'll decide what your preference is, and there's a slight advantage to doing one versus the other, which I'll explain. So if we say f prime of x is equal to the limit as h goes to 0, so now this one, I'm doing f of x plus h first, so that means since there's two x's in this function, I'm plugging in x plus h into both of those spots, so it would be like 4 times, I'm putting parentheses first just so you can visualize. The idea is like both of those parentheses represent the places where x's were in the original function. I'm replacing all my x's with x plus h's. So this now represents x plus h. And then I need to subtract from that f of x, which is just exactly my function. I just got to be careful because there's two terms. I need to put the subtraction in parentheses. And it's all over h. Okay, now once again, I know this is going to be indeterminate just because of the limit, the formula I'm using to begin with. So I don't have to worry too much about that. I know there should be a way for me to simplify and get something to cancel here. So I see lots of algebra I can do. I see I can expand the x plus h squared. I see I can distribute that 5 into the x plus h. So just going to start doing some algebra, okay? So let's see. We have the limit as h goes to 0 of 4, and then I'm going to expand x squared plus 2xh plus h squared. Plus I'm going to distribute, so I get 5x plus 5h. And then I'm also going to distribute that negative, so that's going to give me minus 4x squared minus 5x all over h. I can already see that these two terms will cancel. I can start to see that once I distribute this 4 that I'm going to cancel out my 4x squareds, but let me just do that distribution first before I jump ahead. So then I would have the limit as h goes to 0 of 4x squared plus 8xh plus 4h squared. And then I eliminated those two terms, so I just have plus 5h minus 4x squared all over h. Okay, we're getting closer to an answer. Now I can eliminate there. And something nice that happens in these problems, the quadratics or the power problems, polynomial problems, is usually you're going to see like all of the terms without an h cancel, and you're going to be left with just terms that have an h, which means you could factor out an h and cancel it with the h on the bottom. So that's my next move. So that would be h parentheses 8x plus 4h plus 5 all over h. So those cancel. Oh, I forgot to write my limit. So now I have the limit as h goes to 0 of 8x plus 4h plus 5. This is something I can now plug in 0 for h and not get indeterminate form anymore. Now if I plug in 0 for h, I get 8x plus 4 times 0 plus 5. So that middle term just essentially gets canceled out, and I get 8x plus 5. And that is f prime of x. Okay, so that is telling me a general formula to get the slope of the tangent at any x value. Now remember, if we come back, I asked for it at 2. So then I would plug in 2 for x. So I want f prime of 2 would be 8 times 2 plus 5. So 16 plus 5, and I get 21. So that means the slope of the tangent line of that quadratic function that I started with is 21. So at x equals 2. So what does that mean? That means this is a pretty steep function at that point. And it makes sense because we have like a coefficient of 4 in the original function, which is going to make it narrower to begin with. Okay. Now, that was way 1. There is another way to do this problem. So the next way to do this problem uses a slightly different formula. So in our formula, we had f of x plus h, but we could have also done it with a formula that looks like this. F of a plus h minus f of a over h, and we're taking the limit as a goes to, as h, still as h goes to 0. So notice the only difference in this formula is that instead of an x, I have an a. And the difference between x and a is a represents the specific value, the specific x value at which I'm trying to find the derivative. So if I'm finding f prime of 2, that means a equals 2. Okay? So I could think about this using this formula as the limit. Oh, I have to come up with a function. Oh, no, we're using the same function, right? Okay. The limit as h goes to 0 of f of a plus h, that means f of 2 plus h minus f of 2 all over h, right? So what is f of 2 plus h? Well, I'm just going to write f of x here so I don't have to keep scooting up. F of x is 4x squared plus 5x. So that means plug in 2 plus h in for the x in both spots. So it would be 4, 2 plus h squared plus 5 times 2 plus h minus f of 2, so that just means plug in 2 for x, so minus 4 times 2 squared plus 5 times 2 all over h. So basically what ends up happening is I'm kind of simplifying with numbers within the formula as opposed to doing it at the end when you're like plugging in the 2 at the end. But we should get to the same answer. So let's see what we can do. First of all, like all of this stuff over here is just a number. What number is it? Well, 2 squared is 4, 4 times 4 is 16, and then 16 plus 5 times 2 is 10. So this should all become 16 plus 10, which is 26, right? So I know I'm going to have something here minus 26. And what goes here? Well, I can expand 2 plus h squared. So 2 squared is 4 plus 2 times h, so it would be 4h plus h squared. And then here I could distribute the 5 inside, so plus 10 plus 5h. And then, well, I didn't quite space it out that nice, but all of that minus the 26 over there and h on the bottom, limit out front. Okay. So from here, now I'm going to distribute that 4 in. I get 16 plus 16h plus 4h squared plus 10 plus 5h minus 26 all over h. Limit as h goes to 0. And I'm not going to be too strict if you don't write your limit for every time because it gets kind of annoying. But things start happening now because I see I have a 16 plus 10, which is 26. And then I have a negative 26 over here. So that's all going to go away. And what's left all has an h in it, right? So that's good. I have 16h plus 4h squared plus 5h over h. So I could factor in an h on top, which becomes the limit as h goes to 0 of h parentheses 6 plus 4h plus 5 all over h. My h is canceled. That's the goal. Now I'm taking the limit as h goes to 0 of 16 plus 4h plus 5. I'm plugging in 0 for h, so I get 16 plus 4 times 0 plus 5. 16 plus 5 is 21. And notice, like, this final work looks a lot like the work I did over here, right? I ended with 16 plus 5 equals 21. Here I'm also ending with 16 plus 5 equals 21. Now, you might prefer one way or the other. The quick plug for the way 1 would be that in way 1, it's a little bit more powerful because I have a general formula for the slope of the tangent line, 8x plus 5 at any x. So if I asked you about f prime of 2, but then also f prime of 3 or f prime of 10, this formula could tell me all of those things, right? It could tell me at any x. But if I had to find multiple specific tangent line slopes using way 2, I'd have to do all the work every single time for each different a value, right? Because I'm plugging in a specific value from the beginning. So there are pros and cons of both. That's the last example problem I'm going to do on here, but I do want to give you one U-try problem. So I'm just going to squeeze it in at the bottom. So for the U-try, you're finding f prime of 4 for the function f of x equals 5x squared minus 2x. Okay? So this one, your work should look a lot like either way 1 or way 2 in example 3, but this problem is very similar to example 3. All right, everyone, have a wonderful weekend, and we will be talking about this in class.